Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. It's my pleasure to introduce Professor Ninghui Li from Purdue University, and he will speak on Trojan horse-resistant discretionary access control. Please.
Thank you. Today I'll talk about Trojan horse-resistant discretionary access control, and this is joint work with my student Ziqing Mao and Hong Chen at Purdue University, and also my collaborator Xuxian Jiang from George Mason University. So I was here in the morning attending the talk of Arvind, and I know at least two of you were also there. So actually this is related to that. So near the end of his talk, so his solution to the problem of maintaining kernel integrity is basically you maintain the hash of the kernel code and all the kernel module securely, and then you will only load the kernel code if those hashes are correct. Now the problem is if you use this in a real-world system, then kernel need to be patched. So you need to update, the system administrator need to be able to update those hashes of the code. Otherwise, you cannot update the system. So that means the system has to provide a way for system administrator to do the update. So then a natural way to attack the system is for the attacker to break in, get root privilege, and then change the hash value. So that doesn't require injecting any code into the kernel. So it's not protected by the mechanism he proposed. However, it compromises the security it provides. So in some sense, if any kind of security system you apply, in the end, if you use it in a real-world dynamic environment, this security information must be updatable. So you need to make sure that only the system administrator can do that. And that is part of the thing that the approach we are going to discuss today can help address. So to start, let's just review the basics of discretionary access control. So discretionary access control is what's used in today's commercial off-the-shelf operating system like Linux and all the variants of Unix, and also Windows-based system also use essentially discretionary access control. And it has the advantage that users are familiar with it, and the discretionary access control policies are relatively easy and intuitive to configure, at least when you compare it with other access control approach implemented in, for example, security enhanced Linux and others. However, people know that discretionary access control has some key weakness. So in particular, it's vulnerable to Trojan horse and also to buggy software. And traditionally, people try to fix the problem by applying mandatory access control, which enforce completely different policy from discretionary access control. What I hope to convince you today is that there's a better solution, which is you enforce the discretionary access control in a correct way, and that will be able to solve a lot of the problem. So in order to do that, we have to analyze exactly what makes discretionary access control vulnerable. So we first look at the definition of discretionary access control from the Orange Book, the TCSAC, Trusted Computing Computer Security Evaluation Criteria. So this is a definition. I want to point out a few things that are red here. So we are controlling access of subjects, which are basically processes in operating system. And the access control is based on identity of subjects. It's based on whose behalf these processes are acting on behalf of, are acting on. So this is one feature of discretionary access control. And the other is the controls are discretionary. So a subject with certain right can pass that right to other subjects. So one example is the owner of the file can change the permission of the file to allow other users to access the file. And that's a direct passing of permission. Another indirect passing of permission is a program who can read the file, can make a copy of the file and make that file word readable. So now everyone else can read that same file. So these are the how access permission can be passed in discretionary access control. So to make things more concrete, we will look at how discretionary access control works in Unix. In Unix, processes are the subject, and the security principles, which are the entities that we give right to our user account, which are represented as user ID. And there's a special user account root, which has user ID 0. And every file will have an owner and associated group, and also permission bit, which describe whether the owner can read, write, or execute the file, and whether other users in the same group can read, write, or execute the file, and also every user else. So I assume that everyone is familiar with this. And also a file may have a set UID bit, which will be fairly important. So this describes which user can access the file, but of course the access requests are sent by processes. So we need to, for each process, we need to associate user ID with it. And the key mechanism is every process have an effective user ID, which is identify the user that which user this process is acting on behalf of. When a process accesses a file, the effective user ID of the process determines whether the access is allowed or denied. And when a process executes a load file, so you load a new binary, then there are two cases. If the set UID bit of the binary file is set, the effective user ID is changed to the owner of the file, and otherwise the effective user ID will remain unchanged. So what I want you to remember is that the implicit assumption of this implementation is each process is acting on behalf of a single user because there's a single effective user ID. And later we will show this is actually the key problem with Unix stack implementation. So since early 70s or maybe late 60s, people know that discretionary access control is vulnerable to Trojan horses. So Trojan horses are basically malicious software that apparently have some good functionality but have hidden malicious actions. And you can get this Trojan horse from many different channels. So it can be send an email attachment and you save it and it's a malicious software. Or it can be while you're browsing some website and this download automatically happens and you get this malicious code from there. Or you may be getting it from removable media. You insert a flash drive and copy something from it, and that is actually malicious code. And because of the Unix DAC implementation, when you execute a software, the effective user ID doesn't change. So because normally this file will not have the set UID bit set. So that means that when you execute a Trojan horse, the new process still have your effective user ID. So the new process can do whatever you allow to do. However, it's really malicious code. So you are really giving out your permission to this attacker who writes the code. So that's what's that is certainly a vulnerability because the process is no longer acting on behalf of the user, but it still has the same user's effective user ID. So this problem can be called an incorrect deputy problem, which is similar to the confused deputy problem, if you are familiar with that, but it's slightly different. But basically, this is a problem caused by Trojan horse. A standard example about Trojan horse is you have a highly secret document, and the user is allowed to read the document, but user run a program, which is a Trojan horse. The Trojan horse reads the document and then make a copy and allow everyone else to read the document. So that the secret is leaked. Yes?
So you said that is vulnerable to Trojan horse attacks. Can you give some examples about existing systems, existing access control models that are not vulnerable to Trojan horse?
So, for example, the Bell-LaPadula model that that enforce so it try to maintain secrecy property in face of Trojan horse.
Yeah, any existing real things, real operating systems?
SE Linux and AppArmor at least.
Okay.
Any mandatory access control system will resist this.
No, actually, I would disagree with that. So first, it will depend on how the policy is set up, and yeah.
If you have a programmable policy, you can create a vulnerable policy.
And also, for example, I believe the standard AppArmor policy actually could be vulnerable to Trojan horse. So because when the user log in and get a shell, the shell is in an unconfined domain, right? And when you execute the Trojan horse program, the program typically has no policy associated with it. So when you run the program, it's not confined. So in that case, it can be vulnerable to Trojan. And SE Linux is the same. It depends on how you configure the policy.
So you could create a policy that would resist this. You can also create a policy that says you get to do anything you want, and that won't resist very much.
But the widely used deployment of this SE Linux and AppArmor actually are vulnerable to Trojan horse. AppArmor is for sure.
From the user shell perspective, but
right.
Not from the network daemon perspective.
Right. So that's a different issue. So so this is one vulnerability, and this is another, and some protect against this, but not that. But you are going to see one that. So what we are going to present is will protect against Trojan horse. So in addition to being vulnerable to Trojan horse, existing DAC schemes are also vulnerable to buggy software. So if you run a daemon program, it receives input from network, which could be potentially controlled by the attacker. If the program is buggy, when it receives this malicious input, it could be exploited. And then the process could be taken over. So then this process starts from a buggy with a buggy software. It ends up being Trojan horse. It ends up being running malicious code. So because DAC is vulnerable to Trojan horse, it's also vulnerable to buggy software. And so typically this happens with a network-facing daemon and client, but also could be local utility. So you run a document viewer which open a document and try to render it, and then a vulnerability is exploited, and then the attacker takes over.
Any software which is not too small, buggy?
Yes. So now exactly. So then the question is, how can we deal with this situation? Because the existing DAC implementation works if you assume all software are benign and correct. So if we have that, existing DAC is perfectly fine, or at least that's as good as you can get. So that's kind of the starting point of our work. Suppose we are living in a world with no every software is benign, it's not malicious, and it's correct. It can handle malicious input correctly. Then we are fine. Now the question is, how can we get to that world, given the fact that there are malicious software and the software can be buggy? So probably you all agree with this, but just to drive home, I believe I'm arguing that that DAC vulnerability are the root cause of many of today's security problems. So this is the key reason that end hosts can be compromised. So if you have a warm propagation, that's typically because the end hosts are running some buggy daemon program that get exploited, and then the malicious code gets executed, they take over this host and then propagate. And also, when attacker take over a host, they can install a rootkit, and they can make the host join a botnet. And then, while having this botnet can be used to do spamming, phishing, distributed denial of service, and so on and so forth. So if we are able to make end host secure, in the sense that it's fairly difficult to exploit, then we are indirectly addressing all these other problems, spamming, phishing, distributed denial of service. So as I said earlier, DAC assumes that programs are benign and correct, but unfortunately this is not the case. So we are living in a dangerous world and imperfect world. And so our work is try to address that. So some of you who are familiar with mandatory access control will say, well, mandatory access control is the solution, is the rescue. Again, mandatory access control, there are different definitions of it. And so here we take a liberal definition, which means that there's a system-wide security policy which restricts access right of subject. And typically, they will try to defend against Trojan horse and buggy software. But as we said earlier, it's kind of depending on how you do it. So the earliest work on mandatory access control is probably Bell LaPadula, which try to achieve multi-level security. So we are requiring information are classified into different levels, and any process read a sensitive information cannot write to any channel that is less sensitive, because that may result in information leakage. So the problem with applying that to today's operating system is basically it doesn't work. It breaks today's application, today's operating system and applications, because you do want to allow those kind of information flow. Requiring absolutely no such information flow is not reasonable. So there are many recent research and development effort on designing kind of some variant of Mac to address the problem. So probably the most well-known ones are Security Enhanced Linux and AppArmor. So these are used in today's system, even though they are used in a kind of a partial. They don't do they don't provide very kind of hard guarantee. The policy in the system are designed in order to make the application work and try to minimize the attack surface, but there's no hard guarantee. And also, they are fairly difficult to use. So for example, for security enhanced Linux, early a very strict set of policy called strict policy was designed, and it turns out that for most users, they don't want to use that. So when it was shipped with Fedora Core, the number one question a user asks is, how do I turn this thing off? Because it will break so many things. So later they switch to a targeted policy which offer much less protection. But the most, what I consider to be the most serious limitation of these approaches is they rely on one set policy that is specified centrally, and then everyone will use that policy. If you want to change the policy in some way, you have to be able to understand the policy semantic and make the change. But that is typically very, very difficult. So in the case of SE Linux, there are thousands of policy rules, which are it's a kind of even security expert. It's really daunting even for security expert to understand what is going on. And also for this approach, it's unclear what kind of security property are provided, and the protection is limited. So for example, as we said earlier, there are cases where the standard distribution, the standard policy is vulnerable to Trojan horse. So in this work, we ask the question, can we have the best of both worlds? Can we have both DAC's policy specification, which is flexible and users are familiar with it, and also resistant to Trojan horse and buggy software? And I hope to convince you the answer is yes, it is possible. Then another question, is this perfect? Is this the thing we should do in operating system access control? And that, I guess there wouldn't be an answer for that. So, and I guess you have to make up your own mind. So, so this is the outline for the rest of the talk. So first we'll look in depth at why is DAC vulnerable, and then we'll discuss the design of our own system and our implementation and analysis, and then we will discuss compare with related work and discuss the possibility of applying some idea to Windows. So we all know that DAC is vulnerable to Trojan horse, and it's bad. Now the question is why we have this problem, why DAC is vulnerable to Trojan horse. So I believe the conventional wisdom to this answer is because it's discretionary, because subject with right can pass them. So when I teach security 2 years ago, if you ask this question, this would be my answer. But recently, I realized that is not the case. So why subject with passing the right is bad? So if I allow another user to read my file, why is that bad? That's if I want to do that. So the problem is not because, the reason that DAC is bad is not because it's discretionary, but rather because of something else. So to pinpoint exactly where is the thing that is wrong, we dissect DAC into 2 parts. So one part is the discretionary policy component, the policy specification part. So in the case of Unix, this will be the part about for each file, we have owners and access right. And then we have a policy about owner can change those rights and so on and so forth. And the other part is the enforcement part, which is we need to determine the process identity. So in the case of Unix DAC, this would be the effective user ID mechanism. So our answer to the question why DAC is vulnerable is that it's because this enforcement part. The policy specification part, which is discretionary, is actually fine. And that's where the DAC's advantage lies. So that's because you associate permission with files, and it's easy for user to understand when I'm changing this permission, what does it mean? And we also argue that this is kind of sufficient for the security goal you want to achieve with an operating system access control mechanism. However, the problem with DAC is this implementation. Because as we described earlier, DAC assumes a single principal is responsible for any request in the way that each process has a single effective user ID. However, we consider a process, user A running a process, and this process loads a program written by B. In Unix DAC, the effective user ID would be A. So this means that we are assuming the program is benign. We are assuming that the program will only do what A tells it to do. The program doesn't have any hidden malicious action. So only in this case, effective user ID should remain BA. If we cannot say all programs are benign, then the entities, the principles that are behind any request by the new process could be A, could be B. So either A or B will affect this request. But because DAC maintains a single effective user ID, DAC cannot remember this. And that is the problem. So similarly, if we have a process running with effective user ID A, and it reads input controlled by B, again, in DAC, the effective user ID will remain unchanged because reading something will not change user ID. But this is correct only when the program can correctly handle the input. If the program cannot correctly handle the input, if a program is buggy, then we have to assume either A or B control this process. This process is controlled by one of the two. Any request is sent by this could be A, could be B, but we don't know which. So in both cases, both A and B should be responsible for the request made by the process, but the DAC enforcement mechanism say only A is behind the request. And that is where we have the problem. And that's where DAC is vulnerable to Trojan horse and buggy software. Mm-hmm.
A way to deal with this situation is to run two processes. One is running in the context of A, and another is B, and then they are doing inter-process function calls.
That would
Can that solve the problem?
I don't think that will be really work. So think about how does this how do you deal with this program read one user's file, then what happens? You create another process. So I kind of don't see how it works. You have this process, it reads one file, then what happens? You either read it or you don't read it, right? So you do want to read it, so it doesn't make sense to create two copies.
I see when you talk about data.
If you go to the minimum allowed to both.
Yeah, exactly. That's so the basic idea of what we are proposing is actually fairly simple, and that's essentially what Yuri said. So our answer to this DAC vulnerability is what we call information flow enhanced discretionary access control, or IFEDAC. This is probably not a very good acronym. If you have better ones, let me know. So our design, basically, we keep the discretionary policy component of DAC, and then we fix the policy enforcement because we fix where things are wrong. And the way we fix it is we maintain a set of principles for each process. So each request will be made by a set of principles. And this set is maintained using standard information flow tracking techniques. And then access is allowed only when every principle in this set is authorized to do that, is authorized for the access. So in this case, once this happens, we have both A and B in the set. They can only do things that both A and B are allowed. And this will be resistant to Trojan horse because a Trojan horse, by definition, the Trojan horse will come from a source that is untrusted. So it will come from, when you get it from network, that fact will be encoded, associated with the program. Whenever you execute the program, you will remember this program. You are running a program coming from the network. So that you can only access things that you allow everyone to access. That can only access a word-readable or word-writable document. So let's look at the design of IFEDAC in more detail. An important concept in IFEDAC is the contamination source. So each contamination source represents a channel controlled by a different entity who may compromise the system. And so every DAC user account that a user can log in and is not root is considered a contamination source. So this represents local attackers. So you don't fully trust every user. This may be because this account may have weak password so that the attacker can break in and masquerade the local user. And another contamination source is remote network communication. And we use a single source net to denote all such network contamination. And this represents the remote attacker. And every process and every file may have been contaminated by multiple contamination sources, and this is maintained in the system. And we maintain this using an integrity level. So, so every subject has an integrity level, which is a subset of all the contamination sources, and this represents which who may have gained control over the subject. And for each object, we also maintain integrity level, which remembers who may have changed the content stored in the object. And there are two special integrity levels. One is top, which represents the empty set. So this means that this has not been contaminated. And this means that this is controlled only by root, because we don't consider root to be a contamination source, because root has to be trusted. And the contamination, there's a full contamination, we call it bottom or bot. So this means the set of all users together with net. So if a process is contaminated by this, then we consider it has been fully contaminated. So we track integrity level for subject and object using these rules. When a process is newly created by fork, the process will inherit the parent's integrity level. And if the process receives network communication, we will add net to the integrity level of the process. So this process contaminated by net. If the process P reads a file, we will add the file's integrity level to the process integrity level. We do a union of the contamination source and assign it to the process integrity level. And if P receives IPC data from P prime, we will add the P prime's integrity level to the process P's integrity level, because it could be contaminated by those. If P creates a file, the new file has integrity level the same as the process integrity level. If P writes to a file, the process's contamination sources are union to the file's contamination sources. And if P logs in a user that is not privileged, we will add the user to the integrity level of the process. So the notion of privileged user is because in today's Linux system, many system administration tasks are not really performed by root user. Oftentimes what is happening is you give super user, you use this pseudo program, give a certain user's privilege to run program as a super user. So then those users are considered privileged. So in our model, you explicitly identify which user you consider privileged, and all the other users will be unprivileged, and you don't need to trust those users for maintaining the integrity of the core system. So initially, the first process will have integrity level top. The first process created by the system is init. And when we first enable IFEDAC protection, the files will not have label. So their integrity level, the integrity level for the files are inferred from their what we call write protection class. So essentially, and this is inferred from their DAC permission of who can write to this file. So essentially, we assume that at the time we enable the system is still secure. If this file can be write only by user A and user B, then we consider the integrity level of the file to be the set A and B. Yes? Do you have a question? Oh.
Yeah. So here you list all kinds of situations where you add integrity levels to. You add integrity levels. Are you considering any scenarios where you remove?
No,
things?
there's no removal.
Then, for example, once my program has ever read any data from the network,
yes,
my integrity is permanently changed.
Right. So that is a question that I kind of commonly often encounter when I describe things similar to this. So there are several issues. So there are several kind of things related to that. One is later we will need to describe exceptions to these default policies about access, not about integrity tracking. Because there are cases where you have a daemon process that talk with the network and need to perform some access that are not allowed by the policy. For example, if you allow FTP daemon to log in user, it has to be able to read etc shadow file in order to check user password. So those has to be specified by exception, and that means that you are applying some you are trusting those programs more. You cannot, the system, if you have the exception, the system is not secure if that program is completely wrong, if that program is incorrect. So that's sometimes you have, in order for the system to run, you have to assume higher trust on certain programs, and those has to be specified. So that's one aspect of that. And the other aspect is that even though for each individual process, once it's contaminated, it's never clean. But if you consider the overall system, that doesn't mean the overall system will all be will all be contaminated, because the root is never contaminated. There's no way for you to contaminate the root. So anytime a new process created is still high. So an analogy I use is consider a tree. So every leaf, it dies, it dies. It doesn't go up. But that doesn't mean the tree dies. You can keep have new leaves coming up.
Yeah, I think I agree the argument that once a process is contaminated, it is contaminated. But when you read a piece of data from the network, that doesn't mean that the process is contaminated. If it is just a piece of data and you handle the data correctly, securely, then it is fine.
Yes. So at this work, at the granularity of this work, we don't know whether this process handled that data correctly or not. So therefore, by default, we have to assume it's contaminated. But sometimes we have to assume certain network daemons are able to process correctly, and therefore the integrity is maintained. So one example is if you allow user to remotely log in and administer the system through secure shell. So then you have to say secure shell doesn't drop integrity when it receives network traffic, because otherwise there's no way for you to do it. So then that means we assume secure shell daemon can correctly handle those programs. So when you specify the policy, that is the trust assumption you are making. And the next step, or at least one direction we plan to explore, is whether we can go into the program and being able to better tell whether we should assume that it is contaminated or not. But that is kind of beyond the scope of this work. For this work, we view each program as a black box. So here are some examples a web server will have net at the integrity level because it's contaminated by net, and Alice's email client will have Alice and net in the integrity level. So these are the two contamination source. And if you save a file from the email, then that will have Alice and net. And if you run a PDF viewer and that will have Alice at the integrity level. But if this viewer open the email attachment, then we will add this label to this label, and we get Alice and net. Yes.
Suppose it creates a process.
Mm-hmm.
It goes and reads something,
Mm-hmm.
and maybe gets a Trojan.
Right.
Then process is terminated. I start a new process.
Uh-huh.
So the new process is supposedly clean,
Mm-hmm.
but I have a Trojan in my.
So think about, so you have a process P, it reads these children, so its integrity level include the net in it,
Yes.
and you start a new process by this process.
No. This process terminates,
This process terminates, then who created?
and then I create a new process.
Then that process has nothing to do with the children. It's not running the children code. So this is like in my shell, I run the children program. It's terminated, and then I run ls. Then you cannot say this process running ls is children because it's running ls. It's not running the children code.
But the first one could plant Trojan into.
No, if the first one says write a file ls in my directory, suppose this directory is word writable, this new program will have that label again. When I run it again, I will be contaminated. So basically, the attacker, the claim that we can defend against Trojan horse is the attacker can never control something that doesn't have net. So to determine access, we also have to specify policy for files. So each file has 3 different protection classes. Read protection determine who can read it, and write protection determine who can write it. So each of this is again it's a set of contamination source. So this is it takes the same value as a label, and the default protection classes are inferred from the DAC policy. So for a file, its read protection class is if this file is word readable. So look at the 9-bit permission bit. If it's word readable, then the protection class is bot, meaning everyone can read it, because this is not something you want to protect when you specify it's word readable. Otherwise, you calculate the set of users allowed to read file. So this may be either the owner or user plus the group that are associated with it, but essentially it will be a set of users. And you assign that as a read protection class for the file. And for write protection class, you infer it similarly. And for admin protection class, because DAC policy is only owner can change read protection class and write protection class, so this takes the value of the owner of the file. So the default access policy in IFEDAC is a process is allowed, access is allowed if and only if all the contamination sources in the current process integrity level are authorized. So essentially, you check whether the integrity level of the process is a subset of the read protection class for the file when you are doing reading access, and you do for writing and changing permission, it's similar. And IFEDAC also allows files integrity level to be explicitly changed by the user. So the policy is first only the owner can change the file's integrity level. Also, you can only change the integrity level to a value dominated by the integrity level of the current process. So the motivation to allow this is we have to allow system administrator to download some patch and then use that patch file to patch the system. So when the system administrator downloads the file will have integrity level include net in it. Now, if the system administrator look at this file and determine this is the file I want to patch up my system, the system administrator can log into a channel that has high integrity and then upgrade the file's integrity level to high. I argue that this will not be exploitable by a Trojan horse because if an attacker using Trojan horse can never control a level that doesn't have net, then there's no way for the attacker to upgrade the file's integrity level to a level that doesn't have net. So even though you could upgrade the file, but the attacker cannot do it. The Trojan horse cannot do it. So this is the policy for changing the integrity level. So this means that current process integrity level is a subset, meaning that it's less contaminated than the admin protection class, and also this is less contaminated than the integrity level that I want to change into. So what protection does IFEDAC offer? So our analysis in the paper kind of is not, certainly is not a formal analysis, but it's kind of semi-formal. It's argued that IFEDAC achieved the protection objective of DAC. Basically, if you allow this file to be readable only by root, then it is readable only by root. And any so basically any action will reflect the intention of authorized users. So it is possible for the kernel module to be updated. But if that happens, that must be because a user who's authorized to do that, i.e. the system admin, want to do that. So it is possible a system to be updated, but that must be reflect intention of authorized user. And we believe in some sense this is kind of the goal of discretionary access control. You want to make sure all actions are done by authorized users' intention. So we are able to achieve that, but we have to assume a number of things. So first, we have to assume that when you load our module, the inferred file integrity level are correct. So if you already have a file that has been contaminated, so for example, if you have a program file that is writable only by root, and before you load our module, it has already become a Trojan, then there's nothing we can do. So when you load our module, the system must be secure. And initially, the DAC policies are correct. So if you have your kernel module word writable, have DAC permission word writable, then we are not going to be able to protect you because we don't know that file is supposed to be protected. And the hardware should not be compromised. And the kernel, we have to assume kernel is sort of bug-free because our protection code resides in kernel. So if you exploit a bug in a system call and then take over the kernel, then we cannot do anything. What we can ensure is that if the attacker cannot exploit bug in some other program, get a root shell, and then try to do bad things through what kernel authorized. But we cannot protect when the kernel itself are exploited and the attacker take over a system that way. But in some sense, this is the best you can hope at the kernel level access control system. I don't think we can do better than that. And also, we have to assume that if a legitimate user wants to upgrade a file's integrity level, the decision has to be correct. So if a system admin downloads a wrong patch, but he thinks it's correct, and then he installs that patch, the system is compromised. We cannot protect against that. However, we can protect if the system administrator didn't accidentally download the file and accidentally run it, then it will not compromise the system integrity. And so there are some other detail where IFEDAC policy can be slightly different from the standard DAC policy. So basically, the protection classes in IFEDAC, they can be different from those inferred from DAC. So in our implementation, they are stored in extended attribute, and they can be explicitly set by users. And there are two example cases that we want the IFEDAC protection class to be different from the DAC policy. One of them is what we call an internet directory. So for example, if I want a directory which store all the files that I downloaded from internet, but I don't want any other user to be able to write to my directory. So then, so the DAC permission must be this directory is only writable only by me. only by my user. I don't want to allow anyone else to be able to write to the directory. However, I want to allow, when I run FTP, which will be contaminated with net, to be able to write to this directory. So then what I can do is I can set the write protection class for the directory to be lower than the standard write protection class, which is U, just set containing U. I can write, this directory allows any contamination of U net to write. So then if I run FTP, I can write to this directory. And another case is if we have a privileged normal user, so a user who is given a pseudo root, a pseudo shell at root privilege, for that user, we are essentially trusting that user as a system administrator. So then the startup script file of those users should have a write protection class at the top, because you don't want this user's normal activity to be able to write to that script. If you don't do that, then what could happen is the user, while doing some normal activity, accidentally change this startup script. Then the user can never log in to do system admin again, unless someone else who can do system admin to clear this, to upgrade this for the user. So it will not result in any vulnerability. It will just make the system administration difficult. So it's easy for user to lose system admin privilege if we don't have this feature. Yes?
Is that a problem when you set a directory to be writable by net, but readable from, for example, root or some higher privilege?
Yes, but typically, so you can do that. So first you can, if that directory is only user readable, you can do that for readable as well. You can do that for read protection as well. So you can.
Problem to allow a directory to be writable by the net, but readable by higher privilege.
Okay, so that's a very good point, which I kind of glossed over. Our contamination does not propagate through directory. So if this directory is written by UNet, later some other process reads the directory but not files, it will not be contaminated. And the rationale is that when you write to a directory, you don't control the format of the data that's actually written in the file. The format is determined by the kernel code. So when you write directory, you do that by creating a file. Then what's actually being written are by the kernel code. And when you read the directory, it's also by the kernel code. Because we assume that the kernel code are correct, so we don't consider, I don't think, we assume that you cannot exploit a bug in a program by creating a file in the directory, and that program, simply by reading this directory, is taken over by you. So directory can pass confidential information, that's for sure. But here, for contamination, for the purpose of exploiting bug, we think that is not a channel. So someone else reading the directory will not be contaminated. Crispin?
I claim that any access control system flexible enough to be usable is configurable enough to be configured vulnerable.
Yes. Yes. Just like, yeah. So we are assuming that when user change these permissions, their decision has to be correct. So if the user if the user say, well, my etc shadow file should be word writable, and he changed the permission that way, well, there's nothing we can do. So, did that answer your question, Sure, about the directory?
Yeah, I think I can.
Okay. So what we are, the default policy we have described so far enforce very strict separation among different contamination sources, but it's too strict for real-world system and common practices. And we have to have exceptions. And these exceptions are associated with the program binary. So you associate specific exception with program binary. So, and these exceptions, they all imply some form of trust over the program. So the security property we provide so far does not require any program other than the kernel to be correct. So any program can have bug, and we guarantee security because if you read bad data, your label will change. But in real system, we cannot really afford that. For some program, we have to assume they are correct simply in order for the program to work. So there are two exceptions to subject integrity tracking rule. So you can specify a program as what we call a remote administration point or a RAP. This means that when the program receives network traffic, it maintains its integrity. And a standard example is the secure shell daemon if you want to allow remote system administration. And actually, you can specify the program. So if you don't want to allow any remote system administration, you can specify this daemon maintains integrity up to each individual user level. So that means it will. So let's just ignore that. So if you don't want to allow user to remotely log in and does anything sensitive, you don't have to specify this. So this is up to the system administrator's choice. And also, you may choose to specify auto updater at the remote administration point. And for any program, if you specify it as a wrap, that means that you assume it's correct in processing network input. So if this assumption is violated, the security is gone. So, but this is what happens when you specify a program. Another kind of program is you specify it as a local service point, which means that this program, when it reads files and receives inter-process communication data through, for example, either local socket or pipes or things like that, it will maintain its integrity level. So depending on how you want to use your system, you may want to specify the X server and the X desktop daemon to be local service point if you want to be able to doing system integration through some X application. So it depends on how you want to use the system. And this means that you assume this program can correctly process file and IPC input. So in addition to those two exceptions, you can also specify exception for normal file access. So these are kind of, these imply more limited trust than the two previous cases. So for example, network daemon will typically run at either the net level or a net together with the user, but they need to access to configuration file and log file, which are protected at higher level. So for example, FTP daemon, it needs to read etc shadow file, and email client needs to be able to write to the working directory. So these are one class of program we need additional exception. And another class of program are setUID root programs, because the fact that they are setUID root basically implies there's some additional trust associated with it. So for example, the password file can write to /etc/shadow, but it's running at user level. Because this is a normal user will run the password program to change password. So what we do is we allow object level exception which specify limited trust for this program. So we grant special privilege to these programs, and these programs are enabled when you load these processes at a particular integrity level. So if you are already low integrity level, when you load this process, you will not have this integrity level. You will not get the additional permission. So for example, when you load FTP daemon, you must not be contaminated. Otherwise, you will not get this privilege. So when you load FTP at top level, and then we have this privilege. But when you load any other, so this process will have this privilege. When you do a fork and then load a new binary, the privilege is gone, because the privilege is associated with the binary. When you load a new binary, the privilege is gone. So the assumption, so maybe, so let's first look at some example exceptions that we specify. So for FTP server, these are the exceptions we need. So this is for Fedora Core Linux distribution. It can read shadow file. It can write to this log file that's associated with FTP. And they are also given two capabilities. So some capabilities are granted by default, and others are controlled, limited by our protection module, and they have to be granted by exception. So in the interest of time, I won't be able to talk about capability in this talk. So the assumption we are making for this program that we give exception is either this program handle input correctly, then this assumption are fine, will not affect our security. Or even if it's buggy, when it's exploited, the attacker, we are assuming that the attacker cannot do too much damage by directly injecting payload into the address space. So we are assuming that maybe the attacker will be able to inject some shell code into this program, and then get a new shell, and then try to do the damage. Then, because that means this process will load the new shell code, so then the special privilege are gone. Then the attacker cannot do any real damage. So the only way for the attacker to exploit this special privilege is to directly utilize it in the same address space, which we consider to be harder attack that is harder to do than just injecting a few bytes of or a few tens of bytes for shellcode. So in addition, even if both of these are false, the attacker can inject damaging code. The damage is still limited. It's not like we are still offering higher level security than just a DAC with setuid program, because so for example, if the FTP server is compromised, then the attacker can read the shadow file, which is certainly bad. The attacker inject the code, email this shadow file somewhere within the address space of FTP server. That is certainly bad, but that means the attacker can run dictionary attack, try to recover password. But it's not as bad as if the FTP server can directly load the kernel module into the system, load the rootkit into the system. The attacker still cannot do that because the attacker only have this exception. The damage is still limited when we give only exception to this FTP server. So these are the exception policy we are given to setuid root programs. So for the program that change user password or other information, they need to have these privileges. They need to be able to create a new file in /etc. Because what they do is they actually remove etc password and then create a new one. And they need to be able to write to these files. And there are other special privilege for the other setuid root programs. So in the interest of time, I think I'll skip the two usage case. So this describe how you have email client works. So maybe I'll describe this admin logging usage case. So Linux allows normal user to perform system administration and through the sudo tool, and we call these users are sudoers. And sudoers are, you can specify in IFEDAC, they are privileged users. And that means when this user, when a sudoer logs in, the integrity level maintains. The integrity level maintains at top. It doesn't drop to include that user. The shell startup script for sudoers should be at top. So that means when you log in, when you shell startup script are run and read, you maintain at top. But whenever, so at this point, this user, John, who is a sudoer, can perform system administration. However, if this process read, any of the descendant of this process, if it reads John's normal file, then it will drop to the integrity level of John. So then after that, the process cannot perform system administration. So for a user to perform system administration task, you typically need to do a fresh login, and then you only touch the file that are at high integrity. So our paper contains some kind of semi-formal security analysis. Well, I guess I should more say quarter-formal security analysis because it's really quite far away from very formal analysis. Because our paper is currently under submission, I haven't put it on my webpage. But if you are interested, you can send me email. I'll be happy to send it to you. So in our security analysis, we first define the security goal. We want to achieve integrity and confidentiality. And we discuss different possibilities of defining integrity. And it turns out the ones that make sense or that can be achieved by DAC policy is all updates reflect authorization user's intention. And confidentiality similarly means all declassification reflect authorization user's intention. So it is possible for a file to be leaked, but that must be because a user who is allowed to access the file wants to leak it. So I want to point out that even the Bell-LaPadula mandatory access control model doesn't protect against the user. It only protects against malicious program. If you have a user who's authorized to see top secret information, there's really nothing for you to prevent the user to leak that, because the user can simply remember that information and tell someone else. What you want to protect is the user run some program, and that program is malicious, and then leak the information. So we are offering the same kind of protection, because when you run malicious program, that program cannot access the users, what the user can access. And we achieve this goal under several assumptions, and the main goal is, the main assumptions are, first, there are programs that are explicitly identified as benign. So this will include all the programs that are writable only by root. So anything in your initial distribution that is writable only by root, the system utility, those are benign, meaning that if you run those programs and those programs does something, it reflects your intention. So when you copy a file into another, so the fact that you are transferring information is your intention. So it will not hiddenly send that file as an email to the attacker. And also we need to assume that every program that has been upgraded integrity level are benign. And this benign is also relative to particular integrity level. So a program may be benign for the top level or benign just for you, meaning that other user doesn't have to trust. And also the programs that have exceptions associated with it are correct in processing input. So remember that in the earlier part of this talk, we said DAC assumes that all programs are benign and all programs are correct. So we are basically reducing that assumption to not all programs are benign, only the ones you identify as benign are benign. So if you accidentally download some program, and that program will not be benign. So you will not be vulnerable if those programs are malicious. And we don't need to assume all programs are correct. Only those you explicitly identify with exceptions are correct. So we implement this using Linux security module, and we use extended attribute to store these things. And so we've been using these systems with both the server and the desktop for a few months. And our performance is, the overhead is comparable to security enhanced Linux, because basically the overhead what we are doing is actually, the amount of work we are doing is actually less than SE Linux. So this work is similar at some level to the traditional integrity level integrity models, such like BIBA. The main difference is we are not doing mandatory information flow control. What we are doing can be called discretionary information flow control. And because of that, we have each file will have a different contamination level and the protection label. So for example, if you have a log file, or a system log file, it will be contaminated by net, because the system log daemon will will talk with the network. However, its protection label is still writable only by the highest integrity level, subject to some exceptions. On the other hand, in these models, the contamination of an object determines who can read and write the object. So here, this is a separate. And the effect is this will be mandatory information flow, and this will be discretionary information flow. And also, the integrity labels are inferred from DAC, and the protection label are mostly inferred from DAC. So, and this can be discretionary specified. So every user can change integrity level, can change protection class. unlike in these models, these are mandatory, so only the system administrator can change it. And also, we do not use the linear integrity level. Using that will force all users to operate at the same level. Then you cannot offer mutual protection. You cannot protect one user from another user. So what might be of interest, so compared with SE Linux and AppArmor and another system called Systrace, the difference is they are trying to enforce a newly specified policy. And generally, they're trying to do least privilege. They're trying to give the least amount of access to the process. But it doesn't offer too much flexibility because the policy generally fixed. And if you want to change, it's fairly difficult to do. And what we are doing is we are enforcing DAC policy, but we try to do it correctly. So the policy is still DAC. And compared with Microsoft Mandatory Integrity Control, so this is a feature in Vista. So what Mandatory Integrity Control does is they partition files and program into 4 different classes called the low, medium, high, and system. And the program running at one level, they can only update objects that are at that level or lower. But there's no information flow tracking and the fixed integrity level. So for example, one thing you cannot, so this can generally be used to protect programs that you know are vulnerable and you want to protect. For example, you say Internet Explorer is easy to explore, so it will run at, say, low. Then its damage is limited. But think about a document viewer, PDF viewer, or Acrobat. When it runs, in all this, in kind of this system, their access will be fixed in all this system. Because this Acrobat may read and write arbitrary file depending on the user, it generally need to run at high. But then if it reads a file and it contains the bug to be exploited, then you are vulnerable because there's no dynamic information flow tracking in these systems. So this is also related to our work called the UMIC, Usable Mandatory Integrity Protection, in last year's IEEE Symposium on Security and Privacy. The UMIC work can be viewed as an approximation of IFEDAC, where we only have 2 levels, high and low. All level with this net will collapse to low, become low, and all level without net become high. So it cannot protect against malicious users. So if you have one user being malicious, the system can be taken over because they have to operate at the high level. So I've been thinking whether similar idea can be applied to Windows. And the short answer is I don't know, because I don't really know that much detail about Windows access control. But I can see some immediate difficulties. So first, Windows use thread extensively. So one process, one Windows process may have many threads serving different clients. So then if you do contamination at the process level, the process is contaminated by many, many sources. So then it cannot access anything. So we really need to do tracking at thread level in order to work. However, thread level, there's no guarantee of protection between different threads. So processes are separated by OS, but threads are not. So I'm not sure how to deal with that. And also many resources are stored in registry, so I'm not sure how to be able to handle that. And finally, if we want to do it, we need an implementation, but we don't have such a framework similar to Linux security module for us to do it. So in conclusion, DAC's discretionary policy specification part, we think that part is good. It's easy and intuitive for users to specify. And it's, if you are able to fully correctly implement that policy, it will make the system pretty secure. It will prevent the majority of today's attack. The problem is DAC's enforcement is bad because it assumes any request must have a single principal being responsible for it. And we fix that. We maintain a settled principle for each process. And therefore, we are able to defend against Trojan horse and buggy software. So that will be all. Any other questions?
Have you done any work to get finer grained into what Windows already has a feature that they call Mark of the Web.
That I didn't know. So what does it?
Basically, if you downloaded it via Internet Explorer and you save it to a file, it gets the Mark of the Web. And in various ways, Windows won't trust that file.
Right.
Which is like a very crude version of what you're doing here. And it's not applied automatically.
Okay.
You could imagine that Windows would do that, that every process that touches the network gets Mark of the Internet, and then every file that it creates is considered contaminated. But that would be basically everything.
Yeah. So.
If you turn on that, then the Windows updating will not work. Because
Yeah,
usually people go
unless you mark it trusted.
You trust Windows update program.
Yeah,
you have to trust Windows
that's in his
update.
model. But but everything else would also be marked dirty, and so very quickly every user file, everything would be marked as dirty as possible. And so what the important part of this space is to have more intelligence
about
about how contaminated you are.
Okay.
And that's hard because
Right.
it has to do with figuring out the robustness and integrity of the software that's taking the network input. The postfix mail server is very likely still got high integrity after you send in a mail and you lose the malicious. Conversely, the Pigeon instant messaging client, I don't trust it. And I don't know how you could get the operating system to measure and enforce that.
Yeah, so so I'm collaborating with Trent Jaeger and Somesh Jar and Mike Hicks on a proposal, and which will address kind of related to that, because we are so that project was about retrofitting existing code, but basically we need to look into the code and see how we are able to kind of do more fine-grained analysis and make sure that if we place trust on the program, that is justified. And yeah, so it is a very interesting problem to look at.
Another thing I discovered when I got here is that effectively, at least within those Windows mandatory integrity levels, any process can arbitrarily corrupt any other process.
Right.
So the process boundary assumption that you had on your slide.
No, so that was at least the corruption will have to occur through the operating system, through the kernel. So there is a chance for me to intercept that and mediate that. But for things within a process, there's I cannot even start trying to intercept it. Yeah. So one thing that I didn't fully describe is how do we limit inter-process communication. So there are controls about what is the policy that is inter-process communication. It's largely also similar to DAC policy, but there is one important difference. For example, if one process try to p-trace another process, what we basically need to require is the first process integrity level always dominates the second process integrity level, and that has to be maintained for the whole process of p-tracing, because we don't want to and also the second process cannot have exceptions, so we don't want to be able to gain any privilege through p-tracing. Yeah, so.
I think one of the important and interesting thing to continue to explore is how do you figure out the correct set of configuration, the policy configuration, whether you can automate that or you can formally prove the security of the policy set.
So one part that I kind of always wanted to look into is how to generate these exception policies by analyzing the code. But that so far seems to be fairly difficult. And another thing that we are doing now is we want to be able to compare policy setting in SE Linux, in IFEDAC, and in AppArmor. Because I saw there's this kind of debate of SE Linux and AppArmor, which is more secure. So the SE Linux guy will say, well, we are more secure, but there's no objective measurement of, because, well, you can say your mechanism is secure, but It all boils down to what you have actually specified in your distribution. So what we are trying to do is to analyze what are the attack paths that could occur. So what are the set of programs that you have to compromise in order to break system in different way, and then see under this different policy under SE Linux and the IFEDAC and ARPANET and whether there are differences. So we're trying to compare policies in different systems. But that is something we are currently doing.
Claiming that a Mac system is more secure than some other Mac system is a challenging proposition.
Right. So that's...
The way I approximate it is that if you have some ideal least privilege, the security of the Mac system is how close you can get to that ideal in a policy that you can live with.
Okay.
So by that measure, SE Linux is considerably more secure than AppArmor because there's a whole bunch of ways in which it's more expressive. But that leads you to the question of, can you live with it?
I cannot.
You can imagine my opinion. So whether a given Mac system is more secure than some other one depends on what your ideal is. That if the Mac system's preconceived abstractions match yours, then it can be made very secure. And if they don't, then you have to work hard, and so either the policy is uncomfortable or it's insecure.
So then I guess our goal is, in some sense, less ambitious. We are not comparing the two mechanisms, which one is more secure. We are trying to say, this is your distribution, this is your standard policy. We are comparing the standard policy, which supposedly to be the policy that people can live with. So then we can compare which one actually allows more attack paths than the other. So we'll see. Yeah,
There's a good side in the complexity of Windows. There's something for people like us to do. Things to analyze, to come with new ideas. And now we're going to claim-based access control.
Sorry?
Claim-based.
Who's doing this?
Some people in Windows.
In product division?
I don't know.
Never heard of it.
No?
I think I may have heard of it in academic settings, but I've never heard of it here.
Thank you very much.
Thank you.
Interesting.
Thank you.